Hello everyone, welcome to our series of static time analysis. In this video, we are going to see what is setup and whole analysis and try to answer this important question that why static timing, why is this setup and whole analysis is an integral part of static timing analysis. So with this, we are going to start our video. So before going to start about what is setup and whole analysis, it's important to understand that what are clock storage element. So, if you have already seen our previous videos, you might have understood that steady timing analysis is a method of validating the timing performance of our design by checking all the possible combination of path and try to check whether the timing delay of that path is meeting the timing constraint of our design or not. So, in order to do it, it divides the circuit, it divides the whole design into several paths where the one end, where the path starting point and the end point is a register or a clock storage element. So itself, it's really important to understand that what is clock storage element. So there are basically two type of clock storage element that most of you already know. One is level sensitive or transparent latch, or the other one is flip flop, which is S sensitive. So these latches and flip flop are the fundamental building block of a digital electronic circuits or the sequential logic circuits. They both serve as a memory element which is capable of storing any binary information, either 0 or 1, for a short period of a time. Well, you can say that they sound similar, but they have distinct application and distinct use cases. So I'll start with the latches. So a latch is a asynchronous digital circuit, meaning it can change its output as soon as the input is changing. So here, if you can see that this is a kind of a latch where this is the data input and a clock signal is going there. So if a clock is like this, and as we've already specified here in the definition, that latch is nothing; it's a level sensitive storage element. So here, as you can see, that this particular latch is a high level sensitive latch. So when this clock is high, whatever data is there in the deep pin will goes to the output. So as you can see here, when this clock is high, whatever data which is zero in this case is going to the output. But as soon as this goes to low, as even if the data is changing, that doesn't replicate to the output. And once this clock again goes to the high level, it again started replicating the or started sending the data to the output. So as you can see with this diagram, you can see that our latch is being transparent when our clock is high. In the same fashion, there are other kind of latches also which are transparent when the clock is low. So in that case, there are two cases of two types of transparent latches, which is level sensitive, high level sensitive, low level sensitive, and both of them are asynchronous, respond quickly to the input changes. So the main advantages of using these latches are they are very simple, as latches are relatively very easy to understand and are relatively simple to implement and require fewer components compared to the flip-flop. We'll see the implementation of the flip-flop in a while, but for now you can understand that this is very simple to implement. Again, the other important advantage of latches is that they are having faster responses, as in that the latches respond quickly to the input changes since they are asynchronous in nature. Now we'll come to the flip-flop, which are edge sensitive. So flip-flop is a synchronous digital circuit, which means that it changes the output state only at the edge, either rising or a falling edge of a clock signal. So as you can see here in this example, the flip-flop that we have taken, in the clock cycle, we have taken that's a rises or a positive edge triggered flip flop. Same way, there are other kind of flip flop also, which is negative edge triggered. So if in itself this data that we are going to latch, if it's this flop is sensitive to the negative edge, then that type of flop is called a negative or a fall edge triggered flip flop. So if you'll see here that when this clock edge is high, clock edge is positive, or you can say the rise edge of the clock, whatever is the data is going directly to the output, and then it remain inactive throughout this region. And again, when this active edge, which is called the rise edge in this case, is coming, whatever is the data, which is one in this case, goes to the output, and output goes to one. Again, although our data is going zero after some certain time, but as this particular time is inactive, so it won't, whatever is the data is will not get to the output in this particular period of time. So again, when this active edge came, this data, it sees that whatever is the data that directly goes to the output. So in that case, again, it is one only. So it stays one throughout. So I hope you understand the functioning of flip-flop and latches. So if I'll talk about the some common type of flip-flop, they're basically D flip-flop, JK flip-flop, SR flip-flop, T flip-flop, and many more. So flip-flops are basically used when there is very precise timing is required, or when a synchronization is required within the sequential logic. Like I can give you some example, like register, counter, or some memory element. Some advantages of flip-flop is, as we've already seen, that the first advantage is that it's a synchronous circuit. So we'll get a proper precise timing control to our digital circuit. Second is stability, as it has better noise immunity and less susceptible to glitches. So if this I can this advantage I can explain with this latch diagram that we have already seen. So if there is any noise within this particular region, that noise will also get into the output also, right? But that is not the case here, as our flip-flop is only active for a particular edge only. So the noise impact won't be that much high as what it was having in the case of a latch. So that's why it is having better noise immunity and less susceptible to any glitches in the output. That's a very important feature why most of the application require flip-flop only. Because if there is any glitch, we have already seen in our previous videos that if a glitch occurs to the output, that glitch can somehow give some random data to the output, or it can just toggle the whole state of your digital design. So we tries to avoid any glitches in our circuit. So the one important way to it is to use edge triggered flip flop. Secondly is that's sequential. The sequential means that the flip flops are basically are the basis of creating the sequential logic circuits, as enabling the storage and manipulation of a data over time. So in summary, if I just say the latches are simple and faster but lack synchronization, on the other hand, flip-flop are having synchronization more stable but are more complex also. So they both are used based on their application only. Now with this, we'll move to our next slide, which is setup and hold timing. So setup time is the minimum amount of time that the data must be stable or valid before the clock has arrived to a flip-flop to a reliable capture of the data. Validating the setup time can result in metastability that we've already seen in our previous lectures, or incorrect data being latched to the flip-flop. Now, on the other hand, hold time is the minimum amount of time that the data must remain stable or valid after the clock edge arrives the flip-flop for a reliable capture of the data. Violating the hold time can lead to a data being misread, or some wrong data being sent to the output. So it specify that how long a particular signal must be held after the clock edge. On the other hand, setup is specify that how long the data must remain stable before the clock edge. We'll try to understand this with a figure, but before that, I would like to tell you that violating the setup or hold time, any one of them, can result into unpredictable or erroneous behavior, such as metastability, data corruption. Any glitch can occur to the output signal of a flip-flop, or some wrong data may goes to the output that may result to some wrong behavior in your digital circuit. So in itself, I can say in short, if I want to say, we don't want any setup and hold violation for a correct working of our design. So as you can see in this, there's this clock is there, and this is the rises of the clock. In the same fashion, this is also the rises of the clock. But before some rises, there is some margin which we are saying that our data should be stable before this particular margin, and that margin we are saying it as setup time. So we are saying that whatever data is coming to a flop, it should come before that particular uh, time, minimum amount of time that we are considering as setup time. In the same fashion, whatever data that we have last, so currently here the data that we have last is one, that one should be stable. If this is the clock edge, active clock edge of our flop, so this one should be stable after for a minimum amount of time after the clock edge, and that minimum amount of time is called hold time. So here in this case, if you'll see, that data that is coming to a flop at the edge, at the rise edge, is stable for both setup and hold. So we can say that it's properly captured and latched to at the output. On the other hand, here if you'll see the data is it's properly stable in the setup duration, but it's not stable when within this whole time duration. So if you'll see that data is going from 1 to 0 within this minimum amount of time, so it's violating the whole time. So whole time is violated in the second clock edge. On the other hand, the same data was coming here, but instead of going from 1 to 0 here in the whole time, it's going from 1 to 0 during this setup margin only. So setup itself is violated in the second clock edge. So we can say that this data, whatever data is coming here at that particular edge, is not properly latched by the flip-flop. So now we will see that if such kind of a behavior is coming, and this, as we already know, that this may result into some erroneous behavior, data corruption, glitches, or metastability. So how a tool tries to guide this thing to a STA engine so that they can optimize your design and able to resolve these setup and hold violation that are occurring in your design, or also uh, tell the designer that what all issues are coming. So for that, the tool basically gives you a report, and that report consists of something called slack, which is setup slack or hold slack. So slack basically refers to the amount of time by which a signal arrives at the destination can be delayed without violating the required timing constraint of a particular flop. So if I'll just take the example of this particular diagram here, so whatever data that is coming at that particular flop, so this flop will have some hold or setup requirement. So slack basically refers to the amount of time by which a signal arrives at the destination can be delayed without violating the required timing constraint of a circuit or required timing constraint of your flop. So if I'll just take the example of this particular diagram that I'm showing on the screen. So if this is a capture flop, this capture flop must have some kind of a setup and a hold requirement. So if I'll just say that in a report, it is mentioned that that slag for a particular flop is 1 nanosecond plus 1 nanosecond. So by that we can say that it is meeting your setup requirement by extra 1 nanosecond. So I'll try to explain this in very depth here in this slide. But before that, I will like to explain you about this diagram that I'm having. So here we are having two flop, launch flop and capture flop. We have already understood that what is launch flop and capture flop in the previous slides. So for now, we'll try to understand that there are this static timing analysis tool basically tries to divide this circuit, if this is a small circuit that we are taking, into different paths. So here this path, let's call this as a data propagation delay path and just denote it with some din. Similar fashion, there is some combinational circuit between one register to another register, and that combinational circuit is also taking some time that we are calling as combinational delay and denoting by tcom. In the same fashion, as I've already seen in the previous slides, if I just go back to previous slides, here we are having two kind of timing arc, one from data to queue and another one is from clock to queue. So this clock to queue and data to queue will also take some time. So that also has to that also has to come under the timing analysis of a particular flop. So in the same fashion, we will see that this time from clock to queue we are denoting by some t clock to queue. So setup slag is a slag in the setup analysis. So it's nothing. It's a difference between the required time and the arrival time. So if I'll just say that in this particular example, this is the launch clock which is launching the data, and this is the capture flop which is capturing the data. So if I would like to do the setup analysis at that particular capture flop, whether to see that the data which is being launched by this flop is properly captured by this or not, this capture flop will have some setup requirement. So as you can see here, the same clock is going to both launch and capture flip flop. So the setup time of this particular capture flip flop is the minimum amount of time before the clock edge which is coming to this flop. The data should be stable. So if a data is coming from here at this particular edge, this data is like this data must be coming to this queue pin. So there will be some amount of time which is taken by this clock to queue propagation delay. So here I'm just explaining that what is the required time and what is the arrival time. So here in this example, if I'll just if I'll just tell you that there will be some kind of a delay from clock to queue for the data to arrive at this particular queue pin of this launch flop, and then there will be some combinational delay which this combinational block is taking, and then there will be some setup margin, this setup requirement of this particular flop. So if I just say here, if you'll just see the calculation, this required time is nothing, is the time taken by the clock to reach the capture flop. And the arrival time is nothing, is the time taken by the data to reach the input pin of the capture flop. So it's the time taken by the clock, by the data to reach from here to the D pin of the capture flop. So if I'll just say that time taken by the clock to reach the capture clock is one time period, as both the launch flop and the capture flop is taking the same clock. So one clock period will be the required time at which the second edge is going to come at the capture flip flop. Then the arrival time will be t clock to q, which is nothing, which is the time from here to here, or I can just say from the first edge, when the first edge of the clock came, to the out to the time when the output reaches at the q pin of this flop. Then there will be some combinational delay which this combinational block is going to take, and then there will be some setup of the capture flip flop. So if we'll add all these three things, we'll be getting the arrival time. So if this setup lag, which is clock period minus this whole combinational and setup and clock to queue delay, if this is positive, we can say that this particular path is meeting the timing constraint or the setup timing constraint. If not, then we will see then this value itself will be negative, and that negative value will tell the tool or the designer that how much optimization has to done to meet the timing requirement. We'll see this thing in the next slides and try to understand these things in more detail. Now, we would like to know that what all things that are there which can cause setup violation. So for that, we'll be taking the example of these clock, which is where the active edge of the clock is the rises, and this is the active edge, and this is the setup timing requirement of the particular clock. So if our launch clock is working on launch clock and capture clock, both are working on this active edge on this part on the same clock. So this is the clock at which our launch clock will be launching the data, and then it will be taking some clock to queue propagation time delay here, and then some combinational time, and then it should be stable within this time requirement. If it is stabling after the setup timing of this particular clock, because our capture clock is going to take the data at this edge, then it will be a setup timing violation. So if you'll see that if somehow this data got delayed, it might be because of the uh, clock to queue propagation delay, or there is some big combination circuit between one register to the second register or the launch register to the capture register that is delaying the data. So if this data got delayed, that will impact our setup time. That will impact our setup analysis and will lead to setup violation. On the other hand, if you will see somehow, so the solution for this is somehow if we can advance our data, that will positively impact our setup analysis and our setup lag will be positive. So the issue here was that when the data got delayed, it tightened the setup requirement as data arrival to that particular flop is delayed, and which may cause some negative slack. Solution for this is if we can somehow advance the data, that will relax the setup requirement as data will arrive faster now. We'll see that how we can do it in the further slides. But for now, we will see the other scenario where if clock is fast. So when I'm saying clock is fast, I'm saying that the clock edge at the capture flop is coming before the time at which it should come. So clock edge, as we have seen, was coming previously at this time. But now, because it is advanced, so clock edge is coming at some previous at some fast or some other time. So if I'll just say here, if you'll just see here that the same data which we have, which was previously meeting the timing requirement, if the clock edge would have come at the same time as it was coming previously, our setup analysis will be fine. But here in this case, as clock is fast, we are having setup violation or possible negative slack. So here also, if somehow we can advance the data, we can able to manage the manage we can able to manage the positive slack, or we can get the positive slack and meet our timing constraint. So here also, the main important thing that I want to explain here is that if we are advancing the clock, that will also work as a tightened setup timing requirement, as clock arrival is advanced and may cause negative slack. So with this, we have understood that if clock is advanced or data is delayed, as we have seen in the previous slide, this both is acting as a tighten setup requirement. But on the other hand, if data is advanced, then it is acting as a positive or as a relaxed timing requirement. It helps setup requirement in a positive way. Now you will understand. Now you will understand what is hold slack. So in the same fashion, what we have seen in the setup slack, the same example we are going to take. This is some propagation delay, data propagation delay, some combinational path, and then some clock to queue, propagation delay. So in the definition, we have already seen that what is hold time. So hold time is nothing. Hold time is nothing. It's a minimum amount of time that the data must remain stable or valid after a clock edge, right? So that it can be reliably captured so that the flop can reliably capture the data at the output or at the deep end. Sorry. So the setup slack formula for hold slack is, oh sorry, I should have written it as hold slack, my mistake, but it is hold slack actually. So hold slack is the formula for hold slack is arrival time minus required time. So required time and arrival time is same here, but same as in the definition wise it's same. So if you'll calculate the arrival time of the data is from clock to queue plus some combinational circuit. That is the arrival time of the data. This arrival time of the data should be more than the whole time of the capture, so that we can say that our whole slack will be positive and we are meeting our timing constraint. Or another way we can say that if this time duration, which is from clock to queue and then combination, if this is more than whole timing of that particular capture flop, we can say that data was stable during the whole timing of the particular flop that we have seen in the uh, past examples also, like here we have seen, right? So we are seeing that this data which is coming is stable after the even after this whole time has passed. So so now as you've understood that what is hold slack, now you can move to the same scenario where we can see that what can be the potential reason for the hold violation. So if the data is coming fast, or if I'll just show you with the help of this example, if this is the clock edge at which we are doing the hold analysis of our particular capture flop. If this is the flop where we want to do the hold analysis, so we want to say that this time duration which or the data which is arriving at this deep end should be more than the hold requirement of this particular flop. So as you can see here, that this is the hold requirement of the flop, but this data in the data one is if I just show you, this is the previous data, then this is the new data which is not stable within this time duration. It's changing within this time duration. So as it is changing within this time duration, we are saying that we will lost the data is lost. Or another way we can say that setup is passed but hold is failed. Or in other way we can say it like this also, the data was properly captured but not properly came to the latch to the queue pin of this flop. So the issue here is that we have advanced the data. So we can say that when the data is advanced, or as you can see here, the data is advanced, as in like data came fast. This will work as a in negative for the hold analysis. So it's tighten the hold requirement as data changes faster after the capturing edge, and that may cause some negative hold slack. The solution for this is if we can somehow delete the data. So delayed data will help in positive sense for the hold analysis. So as it relax the hold requirement as data changes later after the capturing edge. So with this, it's I think important to understand the slack calculation of our design circuit. So we have already seen the definition, but just now we will see it one more times. Required time is defined by the timing constant, like your clock period in the setup case, or the hold duration in the hold case. And arrival time is the time when the signal actually arrives to a particular deep end of your flow. So slag is defined as a difference between the required arrival of the signal at the endpoint. So if this is just a very rude definition of it, but it's not exactly like this. It's required minus arrival in the case of setup. We want to see the positive slag, and arrival minus required in the case of hold that we've already seen in the past slides, right? So with this, we'll take this example of this diagram. So here we'll see multiple scenario that if we'll advance the clock, delete the clock, advance the data, delete the data, what will happen and what will be the positive case for setup and hold. So this is the capture edge, this is the launch edge, this is the setup requirement for the capture flop, this is the hold requirement for the capture flop. So slag, as we've already seen, it's a required minus arrival for setup and arrival minus required for hold. So this setup slag calculation and hold slag calculation we have already seen in the past slides. It's this clock period is a required time and this is the arrival time. And here this is the arrival time, clock to Q plus combination, and this is the hold time. So this setup or hold flag can both be positive or negative. Positive indicate that the path meet the timing constraint requirement, and negative indicate that the path didn't meet the timing constraint requirement. Fair enough, right? Now, data. Now, this data advancement, if we are advancing the data, if this data is coming fast, it will tighten the hold requirement, right? Because we want this data to be stable for that particular time duration. But relax the setup as data arrives faster, right? We have seen that if data is not data will be stable if this deepen whatever the data that is coming here at that particular edge. If this data is stable, if we want to make it stable, we want to advance it, right? So it's like one, if you are trying to resolve one thing, other is impacting. So we had to see that like we had to do some trade off between these two things and try to see that what is the actual time or the correct time where the data should toggle. So in the other way, if I just say that for the data only, if data is delayed, if this data I am delaying, it will relaxes the hold requirement. The reason for this is that if this data is delayed, it means that it is not coming here. It is changing its state from 1 to 0 somewhere here. So if it is changing its state from 1 to 0 somewhere here, it is helping in the hold requirement analysis, but it is tightening the setup. Se- it is tightening the setup analysis for you, because here in this case it might not be when data is changing from here to here. But suppose if data is changing from here to here and you try to delay it, it might come from here to here only, right? So if data is coming here, then it will impact the setup violation. So it's like one is impacting the other in the same fashion. Same is happening with the clock advancement. So if clock advancement and clock delay. So if clock is advanced, means clock is coming faster, it will tighten the setup requirement and relax the hold. And if the clock is delayed, means if the clock is coming here, it will tighten the hold but relax the setup. I think it's quite easy to understand with the explanation that we have gone through in the previous slides. So we can say that synthesis of the backend tool uses this slack value to identify the paths for the further modification or the further optimization in a way, if I'll just say. So what happened that what all paths, whatever STA tool divides the whole design in various paths, uh, in the first iteration it guessed that what all paths are having the have positive slacks and what all paths having the negative slacks. Based on the negative slacks, it tries to optimize this in the second, third, fourth iteration. It tries to keep doing it till the time it exhausts its iteration limit, or all the paths are meeting the timing requirement or the timing constraint set in the SCC file. So the amount of negative slack tells the designer or guide the tool about the way to optimize the design, that how much optimization that design is needed. Understood? I hope this is easy to understand. If not, you can just write some comment on the comments and write some question in the comments and we'll try to answer those questions. So now we will move to the next final slide of our today's lecture, which is how we can fix the setup and hold violation. So the solution to resolve the setup violation is, so we have seen that we in the setup analysis we want our data to be stable before some particular time, which is the setup time of the clock edge. So if somehow we can reduce some data part delay or the combinational delay, we can say that our data will come before the required time, which is the setup time. So what all way that with this can be possible? One is if we can simplify our combinational logic, we can design our combinational logic in a way so that it will take less time. Second thing is then we can reorder or reduce the number of gates. By saying that reducing the number of gates, I mean to say that there might be some unnecessary buffer insertion in the data path, which might not require. So if that buffer insertion can be removed, that may lead to some less, or that may lead to reduction in the data part delay. Third is if we can do some architectural changes. Many of the time it happen that your design is working like serially, but you can do some architectural changes to make it pipeline or do parallelism, right? So that pipelining or parallelism architecture can lead to reduction in the data part delay, and that will resolve the setup violation for you. Fourth is upsizing of the gates. So what happened that as the meaning of the upsizing of the gate is you are increasing the driving capability of your cells. So when the driving capability of your cells are increased, you can say that previously whatever, like if the driving capability is increased, the amount of delay that they are incorporating will reduce. So if the amount of delay they are incorporating in the delay analysis, if that is reduced, the whole data per delay can be reduced. So fifth is high VT steps. Many of the time what happens that in our design we might be using high VT cells. So instead we can use some low VT cells. So this low VT cells has some disadvantage of its own, but low VT cells decrease the transition time. So as the transition time decreases, our propagation delay will also decreases. So we can replace high VT cells with normal VT cells or low VT cells, which speed up our timing without disturbing the layout. But there are some bit of disadvantage of low VT cells or normal VT cells also. As with the low VT cells, I mean to say it's low threshold voltage cells which are having low threshold voltage. So as the threshold voltage is less, the leakage current will also be less. But on the other hand, speed will also be more. So this low VT cell has more leakage but more speed also, and comparative to the normal VT cells or high VT cells. Fifth is if we can do some buffer insertion. So many of the time what happen that in these 1 nanometer, 5 nanometer of kind of a design, this wire delay is more than the gate delay. So it's better to introduce gate, and if that's the case, we can add some buffer in the gate to reduce the wire length, and that buffer, the total amount of delay, will lead to the reduction in the data part delay. Other kind of thing that we can do to resolve the setup violation is clock tree optimization. So we can reduce the this data part reduce the we can resolve the setup violation by reducing the clock skew. Many of time what happen that the clock architecture that we are building, it's like that it result into lot of clock skew, or the clock tree stitching that we are doing result into lot of clock skew. So if that clock skew we can reduce the setup violation also. Other important thing is that if we can do clock gating, that clock gating will reduce signal time travel, and that signal time travel, if reduced, it will reduce the data part delay also. One more thing, as you have seen, if somehow we can increase the required time. So in the setup analysis, we have seen this clock period. If both the launch clock and the capture clock is working on the same clock, then one clock period will be the required time from launch to capture. So if that's the case, if we can give more time, like if we can give more clock period, then that will help us in resolving the setup time. So that clock period, when itself, it's easy to say that if we can give more clock period, but that's not always the case because this clock period is defined, or it's specified that this clock period itself is talking about the frequency of your design and at which speed is going to work. So it's already defined. So you have to see that if you can do something in that speed of your design where you want to work your design in. So that are the steps. That are the things. Some of the things that which you can do to resolve the setup violation. So on the other hand, solution to resolve the hold violation is to insert the delay element. So what we want in the hold analysis is that we want our data to be stable for a particular after the clock edge for a particular time duration also. That time duration is nothing, it's a hold time of that particular flop. So if we can add some kind of a delay element within that path of the data that is coming to the deep end of our flop, then we can say that we can resolve the hold violation. So this is how tool also tries to resolve the hold violation. So if there, let's say, if there is some 1 nanosecond of negative slag, negative hold slag is there in your path, and some buffer is taking some zero point 0.5 nanosecond. So it tries to add some two buffer in the path in order to meet the hold violation. But you had to understand that while doing so, this might cause some setup issue also, because we have seen that if you are delaying your data path, that may cause that will act as a that will act as a negative for your setup analysis. So you have to see that this kind of thing is not happening there. So once you're doing this, it will slow down the signal and help ensure that the data remains stable after the clock edge. Other thing that you can do is you can optimize the data path delay, downsizing the data path gates. So what happened that if you are downsizing it, you are reducing the capability, driving capability of the cells. You are doing nothing. You are doing just opposite of what you were doing in the setup. And if you are doing like this, you are increasing the delay of your particular cell. And that delay, if it is increasing, it will result in an increase in the delay of your data path also. On the other hand, you can do some architectural changes based on your requirement or optimize the clock tree, which may also reduce some hold violation. So, with this, we have understood that the setup and hold analysis is an essential aspect of a digital design and timing analysis, and as it's serving the critical load in ensuring that ensuring the proper functionality of your synchronous digital circuit. So the reason for this, as you've understood, is that it setup and hold analysis basically helping us to verify that the data is being captured correctly with the flip-flop or the other storage element in your digital circuits. On the other hand, it also checks that whether that if failing to meet the setup and hold requirement, it it will tell your tool or your or the designer basically if something is not if something is some setup and hold violation is failing. It can result in some data corruption or incorrect operation in your digital circuit. So setup violation can lead to some kind of a matter stability, while hold violation can result in some data being misread at the clock edge. Other thing is that in synchronous digital circuit, where multiple flip-flops have common clock signal, setup and hold analysis help ensure that the data transitions occur at the expected time, at the correct time, at the correct place, and maintaining synchronization across the circuit. It also helps us avoid any kind of a meta stability in our circuit by telling that setup is failed for the particular flop and designer will do some kind of a thing to resolve this, ensuring that meta stability won't occur in the actual hardware. It gives a robust operation like meeting setup and hold requirement, ensure that the data signal are stable and reliable during the sampling window of your particular clock edge. This contributes to the robustness of or the dependability of your operation of your particular circuit. It just gives the designer a edge to a positive edge or a confidence that the design will work. So with this, it's really understandable that how important this setup and hold analysis is, not just for the study time analysis but throughout the design. It's really important, and tools tries to do this setup and hold analysis throughout the design in the same fashion, like as we have seen in the previous video where we were where we were explaining that this STA, nothing less, this setup and hold analysis is done throughout the design at every step of your design cycle. So with this, I think now I might have easily made you understandable that what setup and hold analysis is and why these are so important for the design cycle. So if you like the video and do wants to watch this kind of video further, please like, share, and subscribe to support us. Thank you very much.